And so because it's a strong base, the first thing it'll do in this reaction is it'll deprotonate the carboxylic acid. And as we've seen previously, carboxylate ions are significantly less electrophilic because of that negative charge. Now, if you use harsh enough conditions with LAH, which is in this case going to be long reaction times as well as high temp, then the LAH over time will eventually reduce the carboxylic acid all the way to the alcohol. But due to those types of harsh conditions, generally this is not the preferred way to reduce a carboxylic acid. So what then is the method that we would use? Borane BH3, which you may recall from hydroboration reactions, is a much milder reagent that will perform the same reaction. So you start with BH3 THF, borane, THF, the same reagent we saw previously, and then quench the reaction with acid, and you get the same reduction to form the alcohol. So as far as the other functional groups go, we're going to skip acid chlorides and anhydrides. The reduction of those functional groups is generally not very useful because reducing an acid chloride or an anhydride will also yield an alcohol. And so these reactions work, without any problem. It's just as we've said, normally if you want to have an acid chloride or an anhydride, you're going to make them from a carboxylic acid. Well, given that you're going to get the same product as you would if you just reduce the carboxylic acid directly, there's probably not much point in using two steps if one step will do the same thing. But the other functional groups, esters and amides, can both be reduced, and both give us very, very useful results. So in the case of an ester, again, we can add LAH. And that H minus, we put it in quotes again because it's not a full H minus, but behaves like it. Does nucleophilic attack and forms our very, very familiar looking tetrahedral intermediate. Carbonyl reforms, we kick out the leaving group. However, as a result, this gives us an aldehyde. And aldehydes, we've learned, are more reactive than the ester that we started with. So with this reaction, unfortunately, there's no way you're going to be able to get it to stop at the aldehyde. Again, the aldehyde is more reactive than what we started with. And so if LAH is going to reduce the ester, it's certainly strong enough to reduce the aldehyde. And ultimately, an LAH reduction of an ester will yield the alcohol. But what if we wanted to have this selectivity? What if we wanted to be able to stop this reaction at the aldehyde instead of always going both steps to the alcohol? Is there a way to do that? And with LAH, the answer is generally going to be no. But if we change the reagent and use something that is still better than sodium borohydride, but not as reactive, then it becomes feasible. And the reagent we use for that is known as dibol, or diisobutyl aluminum hydride. So it's still an aluminum-based reagent. structured like this. And if you add it to an ester, the reaction is going to start the same way. Nucleophilic attack onto the carbonyl. But this is where the reaction is able to go in a different direction. So we now have this OR group from the ester along with the negatively charged oxygen from the carbonyl. And oxygen will coordinate to aluminum. And with these two isobutyl groups on aluminum, turns out that these types of intermediates can be stable if you keep the temperature cold enough. Typically about minus 78 Celsius, which we achieve that temperature by using a dry ice bath. If you run this reaction at a warm temperature, this intermediate breaks down, you get the aldehyde, and dibol will reduce your ester all the way to the alcohol. But for some esters at least, you keep the temperature low enough, this intermediate ends up being stable, and then you quench the reaction while it's still cold. Once you quench it, the aldehyde forms, but there's no longer any dibol present to do anything, because not only are you quenching that intermediate, but you're quenching any excess dibol that's present. And so under the right conditions, keeping it cold, you can do a partial reduction of an ester and get it to stop at the aldehyde. Amides can also be reduced using LAH, and the result is very much like it is for the esters. And your amide gets converted all the way to the amine. So the final reaction I want to talk about in this chapter is the Grignard addition. And the Grignard addition, this can take place with esters, acid chlorides, or anhydrides. And it doesn't matter which one we use. The mechanism is exactly the same for all three. The only difference in the three starting materials is the leaving group. Now, we generally don't do Grignard additions to amides. Most amides have NH protons, which are acidic enough that they'll just protonate the Grignard reagent and shut down the reaction completely. But here's our X, and again, that X can be the acid chloride, it can be the anhydride, or it can be an ester. And so if we add a Grignard to it, our Grignard adds in, and we form the tetrahedral intermediate. Tetrahedral intermediate breaks down, and we lose the leaving group. So at this point, not only are the three mechanisms similar for the three different functional groups, but the three mechanisms are identical, because once that leaving group is gone, we've got a ketone. And a ketone, as we've learned back in the aldehydes and ketones reactions, is going to be, again, even more reactive than our starting material was. And so we get another molecule of the Grignard, adds in, O minus here, and upon quenching, we get the alcohol as our product. So again, it doesn't matter which one of the three functional groups we use. all three products are going to be exactly the same. The mechanisms are going to be exactly the same. The only difference based on the starting material is what leaving group we use. So that brings us to the end of acyl substitution. And in the next section, next chapter, we'll get into sort of our last major class of carbonyl reactions, which are alpha substitution reactions.